Hello. Good morning. Good morning. I'm going to discuss this new scientific report coming out of mostly researchers from China. It is about influence of artificial intelligence on higher education reform and talent cultivation in the digital intelligence era. So they're trying to solve the problems of inefficient allocation of teaching resources and inaccurate recommendation of learning paths. So the learning path recommendation is not accurate. Trying to solve this issue in higher education. So this paper proposes a smart education optimization model SEOM using some techniques. We'll look into details now. So they combine an improved random forest algorithm and graph neural networks. So the problem, context and motivation. Higher education is undergoing a transformation driven by digital and intelligent technologies like cloud computing, big data, Internet of Things and AI. Traditional teaching methods and resource management are no longer sufficient to meet the demands of personalized, intelligent and modular education. And the paper aims to address these challenges by proposing SEOM, which optimizes educational resource allocation and personalizes learning paths using AI. So the key mechanisms: random forest algorithm, an improved version of random forest with Adaboost. So this is usually used for classification and regression tasks. However, it has limitations such as overfitting on high noise datasets and interpretability issues due to its black box nature. Random forest. So here the improvement is done using integrating Adaboost. So how does Adaboost work? It assigns weights to training samples, giving more importance to misclassified samples in subsequent iterations. So if one sample is misclassified in previous iteration, it is given more importance for next iteration. It combines multiple weak classifiers into a strong classifier by adjusting their weights based on error rates. So the weight update, weight at t plus 1 is equals to weight at t, which is multiplied by a factor e power minus alpha t yi f function of xi. So yi is the true level, xi is the input, and ft is the prediction at step t. And error rate and weight coefficient. So the error rate and weight coefficient here, alpha m is equals to half log of 1 minus e epsilon m divided by epsilon m. What is m? We need to find out. So m is the mth classifier. So it's a set of classifiers. M is the mth error rate of the mth weak classifier. So the example here, if a decision tree misclassifies a sample, Adaboost increases the weight of that sample in the next iteration, forcing the model to focus more on difficult to classify samples. Well, will not it lead to overfitting? Let's see. Okay, this iterative process improves the overall accuracy of the model. And why use graph neural networks? So graph neural networks are used to model the complex relationship between students, knowledge points and learning resources. So unlike traditional networks, GNNs can capture the dependencies between nodes, students and knowledge points in a graph structure. So we have students and we have knowledge points. So knowledge points here are the modular the modules of knowledge components. These are captured, these dependencies are captured in a graph structure. So GNN updates node features by aggregating information from neighboring nodes. It uses age weights to represent the strength of relationship between nodes. So we have HIL plus 1 node feature update equals to sigma summation over ni 1 over root di dj times WL HJL plus WLL at stage L times HIL. So what is HI here? HI L plus 1 is the updated feature vector of nodes. I and I is the set of neighboring nodes. So node I, we are considering node I, and Ni is the set of neighboring nodes to node I. So the feature update is influenced by the name. Feature update of I at step L plus 1 is influenced by the set of its neighbors. And dj are degrees of nodes I and j, di and dj. So it is inversely proportional, as you can see, to the root over di dj. So it is inversely proportional to the weight. So if a node has far too many degrees, then it is less influenced by each of its edge. Its node feature is less influenced by each of its neighbors node feature hj. And what is L here? Okay, we'll find out. Edge weight update here, Eij is used leaky ReLU, A transpose, and WHI, WHJ. So here Ei is the edge weight between, Eij is the edge weight between nodes I and j. Vector A is the attention vector, and the next one denote concatenation. So the example, in a graph representing students and knowledge points, GNN updates the features of a student node by aggregating information from connected neighboring knowledge points. So this helps in recommending personalized learning paths based on the student's progress and dependencies between knowledge points. Integration of RFA and GNN. Okay. So going back to this equation, L is the current layer and L plus 1 is the next layer. Okay, before talking about integration of RFA and GNN, notice that the edge weight, so this edges, the GNN edges, there are no edges between between two students. So that student-student relationship that could be modeled, but that in this framework they choose not to. They could use peer-peer network or collaborative, some sort of collaborative filtering type thing, but here they choose not to have any student age. So now back to the workflow. So data processing and feature extraction. RFA processes high dimensional student data and selects important features using metrics like Gini gain and information entropy. Then graph construction and node updates. So constructs the graph linking students and knowledge points using the features selected by RFA. It updates node features and age weights dynamically to capture dependencies. Then iterative optimization and feedback. The model iteratively refines the learning path and resource allocation based on feedback from GNN and RFA. So the implementation process, data preprocessing and feature extraction. So this is the figure from the paper. So multidimensional educational resource data is processed to select important features using RFA, as we talked already. Weight adjustment and feature output are performed to prepare the data for graph construction. An initial graph is constructed using RFA features linking students and knowledge points. GNN propagates features to neighboring nodes, updates age weights, and dynamically adjusts the graph structure. Iterative optimization and feedback. GNN outputs guide RFS classify weight adjustments. The model optimizes the learning path and resource allocation through feedback loops. The final output and evaluation. Optimized learning path and resource allocation are generated and validated for performance. So they did cross-validation and side-to-side validation, claim to achieve high accuracy, 85 to 97%, and low error rates. This indicates strong stability and generalization ability in handling multidimensional educational data. Learning path optimization, fitting indices, high fitting accuracy, low residuals, GFI, AGFI, CFI. So it demonstrates its ability to capture dependencies between knowledge points and optimize learning paths. Resource allocation efficiency, abnormal network environment. The model maintains high resource allocation efficiency even in challenging network conditions. Shapley value analysis shows the model's adaptability to network delays and bandwidth bottlenecks. Alright. Comparison with baseline models. So it achieves greater than 95% accuracy in large datasets compared to 88% for GCN and 83% for SPM. Resource allocation SEOM maintains greater than 90% efficiency in high density environments, while GNN drops to 75%. So the limitations they mention here, it has limitations such as high computational complexity and the need for more diverse real-world data. Good features such could focus on optimizing computational efficiency and exploring the integration of emerging technologies like metaverse and immersive teaching. I think also the knowledge points, ages between knowledge points could be modeled somehow, which could help to find the optimal learning paths better and faster. Like known prerequisites like algebra is prerequisite for linear algebra, stuff like that could be integrated into it, could be integrated into the GNN. So this is a cool, interesting paper. Good stuff. I hope you enjoy it.